Ok, c'est bon. Ok. So, hello everyone. I am Misson Dupuy, so I am a maître de conférence here in the ELGLL. And for the second part of the mini school, I will speak about tensor methods for the many-body Schrödinger equation, and in particularly about DMRG. Maybe I will say some stuff about more general tensor networks at some point, but it's not really the focus of my lecture. So just to give a brief outline of my lecture. So at first I will present the many-body equation, namely the electronic Schrödinger equation, and in particular the second quantization. Are there bigger chokes? Yes. And also to introduce the tensor that we will approximate. Then in a second part, I will speak about the low rank approximation problem. So the low rank approximation, so first for matrices. So understand, so it will be basically what Antoine talked about. So it will be the SVD, which is the central tool for the low rank approximation for matrices and for tensors. And so to see what are the things so how to generalize the SVD to tensors, and understand what are the different notions that arise of tensor formats, and which one would be the more suitable for the many-body equation that we are interested in. So that's where I will introduce tensor trains, which is also called matrix product states, which is the ansatz that is used in the MRG. Then, so I will speak about the quantum entropy. So, and the relationship to the MPS approximability. So so yeah, so this will be MPS. Sometimes I will, yeah, so since I'm a mathematician, I usually call it tensor train. So yeah, we'll use both, I think, without really thinking. And then, yeah, so the next 2 points will be first, kind of a theoretical result on the approximability of many-body equations by MPS. So this will be Hastings the real law. So it's which states basically that so if you choose a many-body Hamiltonian, which is one-dimensional with nearest neighbor interactions, then it's ground state under an assumption on the ground state. The ground state is approximable by a tensor train of dimension with scales only polynomially with the number of sites. And finally, in the end, I will speak really about DMRG. So really the algorithm, and also something that yeah. So the algorithm, and also some of the tricks, or yeah, well, not really tricks, but how to make it work when you apply it to the many-body equation. So yeah, I don't say too much for the moment, but this is kind of the program. If I am able to go through all the program, I will try to do my best. Okay, so let's start. So it will be a bit more structured than Antoine's lecture. So no many-body equation. I'm not saying you have no program. I'm just saying it will be more structured. So, yeah, so equation and discretization. So the operator that I'm interested in is the many-body Schrödinger operator, which is written like this. So it has a kinetic part. It has also some interaction with nuclei at position RK, and there is the electronic interaction between the electrons. And the problem, so I've put an N here just to emphasize that I'm looking at the problem with N electrons. And the problem that I'm interested in is finding the ground state of my many-body Hamiltonian, and so written as a variational well, in its variational form, what I'm looking for is the minimization of the Rayleigh quotient. Yeah, let's write it as a quotient, where psi is the antisymmetric L2. Yeah, I mean, we can put spins as well. It doesn't really matter. Up. So it's the usual many-body. So it's it's just the space where the electronic wave function lives. So the way to solve this problem, what you would do is choose. So you would choose a finite dimensional vector space to approximate this problem. So you would use a Galerkin approximation. And the Galerkin approximation, so you won't, well, here you won't pick anything too fancy. What you will do is, since you see this, so yeah, here maybe, so yeah, if there are things that are unclear also, don't hesitate to stop me and ask some questions. So here it's the antisymmetric L2 space. So what is rather reasonable is to pick a basis for, or at least a numerical basis for the single L2 space, and then to write the many-body wave function, you approximate it by antisymmetrized functions of one variable. Okay, so what you do in the first step is pick yeah. But yeah, well, we can call them orbitals. So pick orbitals that I will call phi I. So this, I will take L of them, which are, and phi I belongs to the single particle space. Okay. And I assume that they are orthogonal. Then the approximation space that I will choose to approximate this big L2 space is the following. So it will be in which, yeah, okay, I'll put it this way. So this will be what? It will be the span of, well, I write the formula. And so this is what I mean. Maybe so it is just the antisymmetric product of the phi I. Usually you can also, well, in chemistry textbook you can also write it this way. It's the same thing, and it's the Slater determinant of these n orbitals. And so numerically, what you would do is then to instead of solving, well, to approximate this problem, you would solve now this variational problem, but by substituting this big antisymmetric L2 space by this one. Okay. So the approximate problem becomes, so it's this one. I think I've put an L there. Okay. So now I'm looking for a psi which belongs to this big space. And this is what is usually called the full, well, this energy. This will be the full Ci energy. Okay. And so the method that I will present later, so it will be about computing, or at least trying to compute this value here and the corresponding wave function. And so in this case, the approximate ground state it will be written as some sum of coefficients times these Slater determinants. Okay. And so, yeah, so now let's just look for a moment at the number of coefficients we need to parameterize this approximate wave function. So here you will have of the order n choose L coefficients. And so you realize that n choose L is a huge number. So then basically all the methods that try to solve the many-body Schrödinger equation relies on a sparse on a sparse parametrization of these coefficients. So maybe just let's mention a few. So to solve numerically the full CI equation, we need a sparse parametrization of these coefficients. So, well, an idea that is, I think, as old as quantum chemistry is just to select these coefficients with respect to a reference. So usually you would take the Hartree-Fock reference, and then for these coefficients, you say, well, they can depart from 1, 2, 3 or more coefficients, and this is the whole family of the CI methods. So you have the CI methods. Then another way would be to instead of which has its perks. Then another idea would be, well, take maybe something which is a bit more complex, and instead consider a nonlinear parametrization of this coefficient, but which is still sparse for numerical reasons. And this is basically Kleppel cluster. So I mean, it's one choice of doing a nonlinear parametrization of these coefficients. And then so this is this is more so from what I look. It looks like it comes from the 1960s. And then the method that I will speak about in this lecture is DMRG. So DMRG, so the first formulation of DMRG was by White in '92. But it was for systems which are translationally invariant, so which are coming from statistical physics. But it was applied to, so this was for statistical physics. And then it was applied, I think, in 1999, still by White, for quantum chemistry problems. So it's something which is quite recent. And the idea that is behind the DMRG is to use. So at first it wasn't presented like that, but later it was realized that it has been realized that the main idea of DMRG was to use a particular tensor parametrization of these coefficients, and this parametrization is exactly the matrix product space. So to see, the tensor that is approximated in DMRG is not this one, because the idea is to instead of parameterizing these coefficients, what we are going to do is parameterize the representation of the wave function in second quantization. So I will present briefly the second quantization. Okay, so 2. Second quantization. So I mean, I think I will be quite quick about second quantization, and I will present the Fock space and the creation annihilation operator without I mean, I will write them, but without commenting too much. What I will then stress on is about the parametrization of the wave function in second quantization, which is really what I want to what is important for the parametrization by DMRG. Okay, so the Fock space that I will present is the discrete Fock space, because I want everything to be finite dimensional. It's easier. So the discrete Fock space that I denote by this, it will be the collection of these spaces. It will be the collection of the empty, so it will be the direct sum of the empty space, the one particle state, and so on and so forth, until the fully occupied one. And so, so a wave function that belongs to discrete Fock space will have components in each of these spaces. So it looks strange at first well, at least to me, let's say, maybe you are more used to that. But it looks strange to work in this Fock space because here you introduce many spaces that have well, that are in fact useless because you already know that your wave function, your target wave function has n electrons. So it looks a bit strange, but yeah. That's really the purpose of this is really to be able to do a tensor parametrization by tensor trains. So that's the main goal. Okay, so I have my discrete Fock space and and I have creation and annihilation operators. That enable to go from one of these space to the previous or to the next one. So they are defined on the Slater determinants this way. So for the annihilation, you go from written this way. So you go from the k+1 particle space, you go to the k particle space, and and you map to so 0 if I does not belong to one of these ij. And otherwise, it's -1 L -1 pi I1 wedge. So there's one that is missing, basically. I think that's something like this. Where IL equals to I. Yeah.
That's the K or that's the M?
So here it's L, the last one is K. Yeah. Yes. Where the F one is the one that is being destroyed because it's equal to I. And and here implicitly I've assumed that this is normalized, so there's no normalized constants.
Then why don't you call the operator AIL?
Because I mean, if I does not belong here, to rule out the case. I guess just a matter of. I mean, the definition is not so important for what I mean, you can find it in any textbook. And for the creation, it's kind of the same thing. So you go from in reverse. So instead of doing instead of going to the k+1 to the k particle space, you go in reverse. So you go in reverse, and so this is the so you create a particle, and basically you can create a particle if it's not occupied. So so this is So here the normalization factor is so here the phase factor corresponds to the case to this condition. And it's 0 if it's already occupied. So you cannot create the same state twice. Yep.
I is different from IJ.
For all J.
the -1 is to ensure that any new state you put to the left.
Yes, yes, you put any new state to the left, yes. I think it's the most, I don't know, common one. I mean, that's the one I read, so. Yeah. You have also commutation rules about these creation and annihilation operators, which, yeah, well, I can write them since it doesn't cost too much, but so then you have commutation rules. So the commutation rules are the following. So if you apply two creation operators, yeah, no, yeah, these two they anti-commute. So yeah, so this means what? Just to so it's up. So this is equal to yeah. So this is 0, and if you apply I dagger HA, this is equal to I'll put it in the right order. No, yeah, it doesn't matter. Yeah, it doesn't matter. Yeah, yeah, it doesn't matter. Okay, so they satisfy these rules. Yeah. Okay. So these, yeah, these will be useful just to write the Hamiltonian afterwards. But now let's come back to the wave function. So now let's see how you write a wave function in this Fock space. So the thing is, so we want to write this thing in the so we want to translate this in the Fock space there. So the first thing that we are going to do is first to rewrite these Slater determinants. So we are going to first reparameterize the Slater determinants. So I introduce a new notation, which will be this capital phi. And yeah, so it will be a capital phi index mu, where mu will be a collection of L indices, mu1 to mu L, and each mu I will be equal to 0 or 1. And this is what? This will be simply the Slater determinant where the mu index is equal to 1. Okay. So yeah, I mean formally it should be a mapping, but yeah, I think it's more yeah, it's more puzzling when you write it as mappings between different spaces than just writing the formula like this. So it will be something which looks like that, okay, where so So I1 to Ik are exactly such that mu Ik is equal to 1. So I will just give an example. Just say what it means. So, example. So let's take, for example, EL equal to 6, I don't know, and let's see what this Slater determinant is reparameterized in this form. In this form, you write it as phi of, so since L is equal to 6, I have 6 indices in my capital phi. So the first Slater determinant is occupied. So I put a 1. The second is occupied. So I put a 1 as well. The third one is unoccupied, so it's a 0. Fourth one occupied, and the last two ones are unoccupied. Okay. So it's just a way of writing Slater determinants in as occupied or unoccupied states. Okay. Yeah. So this is this is an important point. It's once you have So this choice of this choice of parameterization depends on the way that you have ordered your orbitals. Okay. So here I decided to order. So ordering the orbitals is that I have a phi 1, a phi 2, and so on. So if I reorder these bases, then my parameterization will change. So this is an important point for later in the tensor train. So I will come back to that, but yeah, it's an important point to make. This parameterization is tied to the labeling or the ordering of the one particle basis. What? I mean, I think you have because you are working with this tensor anyway. So I mean, it depends what you are doing, I guess. But since you are dealing with this tensor, I guess the way that you write the tensor depends on how you choose the one particle basis. Yeah. Here, that's true that you would get a phase compared to bosons. Yes, that is true. Okay. So now I reparameterize my Slaters using this phi mu, and so now a general wave function psi in my discrete Fock space will be written as a linear combination of all the possible determinants that I can build using my one particle space, my one particle basis functions, and this then I write it as the sum of the C mu. So yeah, these coefficients are not the same as there. Well, not the same in the sense that they are not parameterized by the same thing. And the mu, the mu, so it will be the collection of mu1, mu L, and the mu I, they are equal to 0 or 1. Okay. And so if I look at how many coefficients I have now, I have 2 to the power L coefficients to parameterize. Okay. Yes. Okay. Okay, and the I1 to IK are the ones such that the mu IK are equal to 1. And all the other ones are 0. So I think, okay, the definition is clearer if you look at the example. If you look at the example, I mean, it's clear that the ones correspond to the phi that appears in the Slater determinants, otherwise it doesn't appear. Yes?
That we don't need to find space where we are working on, but I know it's like what's that parameterization? I mean, from where to where, not really seeing the point.
Because technically this one lives in the L2 antisymmetric space of K particles, whereas this one will live in all Fock spaces. So it will be the restriction to the K particle space of this function, which is equal to that. I mean, it's already, yeah. I mean, yeah, don't pay too much attention to that, but yeah, there are some, well, I think it's more, yeah, it's more, I think it's when you are looking at details that it matters, otherwise you can be kind of, yeah, sloppy with the way you handle things. Okay. So yeah, so I have my general wave function. And the thing that you can see is that, I mean, if I write it this way, I don't impose any condition of my coefficients, then it becomes a wave function that can live in all the sectors in my Fock space, and we are targeting. So it looks a bit yeah, a bit stupid because what you target is an n particle state. So if you want to rewrite the electronic Schrödinger problem at the beginning, you need to do, well, you need to take that into account. So when you rewrite the original problem, then you need to take that into account. The way to take that into account is to add a constraint on the wave function. You add this constraint by introducing the particle number operator. So this, yeah, which will be this operator here. So what this operator, what is this operator doing? So what it does is that basically, if a state is occupied, it destroys and it recreates. So so now if you act, if you apply this operator to a state which has K particles, you see that yeah, I mean, yeah, maybe it's clearer if I apply it to a Slater determinant. So let's apply it to a Slater determinant. So if I apply it to a Slater determinant, I will use K. So for each state that is occupied, it will return the same state. And since I have I have K orbitals that are occupied, this will be equal to the same Slater determinant multiplied by K. So basically, it just separates yeah, all the sectors in my discrete Fock space. Yeah, something that I should have said maybe earlier is how the Schrödinger operator looks like. So the many-body Schrödinger operator in second quantization. So it has a nice sparse structure. So it looks like this. So Ij from 1 to L. Ijkl from 1 to L. Lk. Okay. Where so it has a nice one body and two body structure, and these coefficients here are the one electron integrals, and the coefficients here are the two electron integrals. Oops. But yeah, it doesn't see the particle number. So now so in the second quantization, the equivalent of the problem that I just erased is the following. So now this is equal to the minimum of psi belonging in the Fock space of psi. Yeah, I think I will put a hat here. So under the constraint that psi is an n-particle state. Okay. Yeah, I forgot the normalization. Okay. So the thing with the tensor formats, and especially for the tensor train format. So in the tensor, well, for DMRG and tensor train, we are trying to approximate this tensor, but we want to solve this problem in the end. So the fact that we are targeting an n-particle state will have a consequence on the shape of the tensor, and also the shape of its tensor approximations. So it's something that you need to deal with when you are really solving the problem on a computer, but it's not an aspect that I will speak about. Yeah, just know that in a standard DMRG, that's something that is handled, and yeah, it just means that the coefficients that appear here, they have a particular structure that you need to take into account. Yeah, that's it. And so now, basically the goal for until I speak about DMRG again, it will be how to approximate this tensor by a sensible format, and I think a natural way to look at this approximation problem is to start from a problem that we know how to solve. So it will be about matrices. Okay. So now the goal. At least until I introduce tensor trains, it will be to see how to approximate these coefficients C mu Yeah, you can put them real efficient. For the MRG, no. For the MRG, no. Not as far as I know. Yeah. We speak about, yeah, don't spoil. Yeah. No, well, yeah. I mean, there are reasons, let's say, but maybe it could be doable also to rewrite everything. Okay. So now let's speak about the low rank approximation problem. Yes.
So it's a very general question. You said that usually we expand the n electron wave function into n electron space. But what can we say about the completeness of the basis for the n-1 and n+1 problem? So if I want to have the n electron ground state of function, would I be able to expand it in the n-1 basis or n+1 basis? Will it be complete?
I mean, I don't think that's what you want to do. I mean, because you.
If I want.
Yeah, but.
Should I expand it on the union of the n-1 and n+1 basis?
I mean, okay, maybe it's because the way. So when I say the n particle basis, I'm really thinking of a function which has n. Yes, and so yeah, I mean. So and
we are using this time, we want to access the n-1 and n+1.
Yes. Yes.
Starting from the n.
Yeah, but then you would okay, but then you would I guess you would use the n particles ground state as a reference to yes in this as a so I mean I don't know. Yeah, I don't know here how you would do that, but I think what you would like to do is then change this constraint. Basically, if you would like to target other states with other particle numbers, and then you would apply the MRG with this different constraint. Yeah. Yeah, I think that's what. Well, and it's more like if you are looking at the ground state of n-1 n and n+1 electrons, then you could have an n electron ground state, a pure n electron ground state, and not a mixture of states. I think that's, but yeah. So basically, it means that you would look at a different constraint and work with the MRG with the different constraints. I think that's what you would do. Okay, so low rank approximation problem for matrices and tensors. So first thing, matrices. So for matrices, in fact, the solution is given by the singular value decomposition that Antoine spoke about this morning. So I will introduce the SVD. So I will consider a matrix A. Let's take it real. Then the SVD of A. It's simply A that you write A where so this has dimension m times r, sigma R times R and diagonal. And V, it has size N times R. And you have additional constraints. So you have that U and V are orthogonal. So when they are non-square, yeah, orthogonal means that, yeah, is that you have only one side where it works. So it's the side that is the smallest, and it's this one, this R. So, so with U transpose U equal V transpose V equal identity of R. Okay. So the nice thing about DSVD is that, yeah, so Antoine spoke a bit about it, but with DSVD, you can directly see the rank of the matrix. The rank of the matrix is basically the dimension of the matrix that is sitting in the middle. So this sigma here. Yeah, and something also that I haven't said is that this sigma, it has only positive values. Okay, and all the sigma I are positive for all I. Okay. So sometimes, I mean, okay, sometimes you present the SVD avec with square matrices as for U and V. So this one is sometimes referred to the compact SVD, but yeah. So Antoine presented the proof, so I don't have to redo it. Yeah, one thing that he mentioned, and I can mention again, is that these singular values, they are in fact related to the eigenvalues of the matrix A transpose A. Okay, so if I do a small calculation, so A or A transpose, I mean, they are related to both. So if I do the computation, what I find is that so here, since I have this condition, this is simply U sigma square U transpose. And so here now you can kind of read that this is the eigenvalue decomposition of AA transpose. And so these are the positive eigenvalues of my matrix AA transpose. Okay, maybe some examples. Maybe so maybe let's consider a 2x2 matrix, so that I write it this way. So yeah, so first question, is it a singular value decomposition? It's a
Sign of lambda.
yes, yes. So yeah, I mean it's almost the singular value decomposition. It depends on the sign of lambda. Okay, so just be careful about that. So if lambda 1 is larger than lambda 2, then this is DSVD. Otherwise, if you have a sign change, then you will have to flip the sign of one of the columns. Okay. So if, for example, you are in this case with, let's say, this larger than this. So another thing that is quite common also that I have not written in the definition is that usually we like to order them in magnitude. So, and the first So the first singular value is larger than the second one, and so on and so forth. Okay. So it's yeah, it's something that I haven't said, but yeah. Yeah, usually, okay, in my notation, Q is orthogonal, unless I forget. But yeah, Q needs to be orthogonal. That is true. Yeah, in this case, you will have to flip the sign. So to get the SVD of Q of A, then if I might write my matrix Q like this, then I will have to flip the sign of this one. Yeah, maybe I should have written this. Yeah, I will write it there. And I have Q1 transpose, Q2 transpose. And so if I do the math, then I happen to find the same matrix. Okay. So the thing that makes the singular value decomposition remarkable is not only that it reveals the rank of any matrix, it is also related to the best approximation problem. So this is the best approximation. So if I consider, so I consider a matrix which is of size m times n, then yeah. So the minimum, yeah, maybe, okay, well, I will write the results, and then I will comment. So, I mean, mathematically, it's this. Okay. Yeah, okay. I think I realized that I forgot to write a few things. Okay. Yeah, so first maybe the norm. So the norm that I'm using. So since I'm talking about tensors, I want a norm that I can apply to any kind of object. So I'm using the Frobenius norm. What is the Frobenius norm? It's just the L2 norm when you see the matrix as a big vector. Okay, so the norm of A Frobenius, it's just the sum of all the entries of my matrix. Okay. So in other words, it's just I see my matrix as a long vector, and this will be it will be the natural norm if I want to study tensors of any size. So what does this mean in mortal terms? It's just yeah, I mean, I'm looking at the best approximation of my matrix A by a matrix which has at most rank K, and I can characterize this problem first as a solution. The solution is given by the first K modes of my matrix. Okay, so yeah, so it's structured, but not so much. So another way to write this thing is to write it this way. So I write U as U1, UR, V as V1, VR, and if I just unveil what is this matrix products, I happen to find my sigma I and my VIs are quite similar. Okay. So this is also another way to see the SVD, is to see the SVD as a sum of rank 1 matrices. Of rank 1 matrices. So this is a matrix which has rank 1 because I multiply a column vector with a row vector. So this gives me a matrix. And so what this theorem says is that the best K approximation of my matrix A in the Frobenius norm is by selecting the K first modes of my matrix, okay, the K dominant ones. And the error that I'm making is just of the order of the singular values that I don't take into account. Okay, so there are two remarkable results. So first, there is a best approximation, and second, we can characterize what is missing in my best approximation. So if I take one more rank, I will capture sigma K plus 1. Okay. And its rank of AK is equal to K. Okay. So so we'll do a proof, but we'll do a proof not for this norm because it's a bit cumbersome to do it in this norm. In fact, the same result holds true for the two norms of the matrix that I will say, well, that I will introduce. And in this case, it's much simpler. So proof. For the spectral norm. For the two norms. So the two norm for the matrix is just the supremum of this of the two norm of the vectors. Okay. And so the first calculation that we do is just A minus AK in the two norm. So AK given by the formula over there. So I just use the SVD. And if I use the SVD, I get this. It's R. And now, I mean, to just read what is the two norm of this matrix here, I just look at these vectors. These vectors, since my matrix is orthogonal, all the columns of U and V are orthogonal. So, so basically, if I apply a vector, I mean, what will come out? So if you do, so what will come out is that it will be smaller than the largest mode, and so it will be exactly so the supremum will be exactly given by the K plus 1 singular value. And so now we just need a lower bound for any matrix of rank K. So we take some A tilde K. So a matrix of size n times n, which has rank K. So now, yeah, the trick is just to see that since this matrix is of rank K, I can consider, for example, some W in a span of K plus 1 vectors. So the vectors that I will pick are the vectors that are associated to the largest modes of A. Okay. So it will be a let W in this span such that, so since it's a matrix of rank K, I can find a vector which is non-zero such that if I take a K plus 1 linear combination, this is 0. So such that AW is equal to 0 and W is equal to 1 in the 2 norm. Okay, because here I just have K independent columns, and then here I have K plus 1 degrees of freedom. So this vector exists. And then I just, yeah, it's tilde K, yes. Then I just compute A minus A tilde K W. And so this is what in the 2 norm. So by definition, this is just the norm of AW in the 2 norm. So this is the, now W, it belongs to this, so it will be, so it will kill all so by orthogonality, it will kill all the modes that are above K plus 2. So it will be up. So it will see only the first modes. So here it's Pi transpose W. Up. So this is a scalar. And then, well, this is then smaller than so these vectors are orthogonal, and this vector is normalized to 1, and yeah, well, the sum of, well, W is normalized, these vectors are orthogonal, and so if I compute the 2 norm, what I see is that this, and since, yeah, sigma K plus 1 is the, no. Yeah, okay. I want this sound like this. Okay, W belongs to this span. And this is, yeah. Okay, maybe I should just write it. So this is larger than, yeah, I'll put squares everywhere. So, so this is larger than this because sigma K plus 1 is smaller than this. And the sum over I of this vector, this is exactly the norm of W because it belongs exactly to this space. So it will be equal to sigma K plus 1. Okay. Yes. Here. Here, I mean, so I'm looking at the 2 norm, yeah, the matrix 2 norm of this. And so if I apply any vector, any normalized vector, then since these are orthogonal, I will just get the components. And so it will be smaller than sigma K plus 1. It will be equal to sigma K plus 1 exactly for the vector Vk plus 1. Yes? Yes. No, it's important because basically, so now I take a candidate A tilde. So I take a candidate A tilde. No, it works. I mean, no, it's exactly this span, because if I want to apply it to AK, I would take, for example, something that is on V1 to have this property. Yes? I don't know. Is it fine? Okay.
So the nice thing with this theorem is that you know that to truncate at let's say at long k, or the case value, you know that the error is just what is missing, and just the sum of what is there.
Yes.
Other than you expect that this is slow, but you don't have any idea of the slope of just like
Yeah.
I understand that maybe there are 1,000 of this.
Yes. Yeah. So
So you don't have access exactly at this estimate.
not exactly, but at least you know what you are looking for. So if you want to, so if you have any kind of matrix, then what you want to be able to say is, has my matrix a strong decay in the singular values? If it has a strong decay in the singular values, then I know that I have a low rank approximation.
But first, you put all the singular values. So
well, you need a bound. If you are able to bound the tail of the singular values, then you are fine. Yes. So yeah, what you are looking for is then a tail. Okay. But that's a good remark. I mean, the remark then becomes is, are you able to characterize the singular values? Yeah. Okay. Yeah. So first thing is, yeah, maybe I could have commented the theorem before doing the proof. Is that yeah, in what sense this is a low rank approximation. So what is the dimension reduction that you have? So dimension reduction with the truncated XDB. So yeah, so usually this guy over here, you will call it the truncated SVD. Yeah, so you start with the, so A is a matrix of dimension m times n. So it has m times n coefficients. And with the truncated SVD, you would need to just the singular values and the vectors ui and vi. So you would need k times m plus n times k plus k coefficients. So k times m, this is for the ui. So this is for the vi, and this will be for the sigma I. And so if M and N are very large and K is much smaller, then you have somewhat, well, you have achieved a reduction of dimension. And so, as Emmanuel was pointing out, you can achieve dimension reduction if you have a decay, a strong decay in the singular value. Okay. So the best approximation is a good approximation. So if the singular values decay fast. Okay. Yes.
Are there other compositions that can achieve something similar? I am thinking maybe QR decomposition is something similar.
Yeah, I think so. By
can you use something different than LVD?
Yeah. I think you can do also Cholesky probably if A is symmetric. You can do yeah, if you remove all the positive things, I mean you can.
It's a triangular matrix. Yes. But then what can be used as an assessment of what is small? There is no.
I mean, probably it's relative. Well, it's related to the size of the diagonal elements, but I don't think you have something as clear as this one. Yeah. Yes. Mm. Okay. So maybe just before I go to the generalization of tensors, so you have this best approximation point of view where you write A as a sum of rank 1 matrices, and you are looking at what is the best approximation of my matrix as a sum of K rank 1 matrix. Another way to see this SVD, and in fact to see this problem, is more in terms of subspace approximations. Okay, so yeah, so I will write it. So so in fact, another way to write this problem is to write it this way. So you are looking at so still in the Frobenius norm. So what you are looking at are two matrices which have well, dimension so rank K, and you are looking at the product that minimize the distance to the matrix. And I mean, you can kind of convince yourself that this is exactly the same problem as here. It's just I have written AK as the product of two rank K matrices. So this is exactly the same problem, and the solution will be exactly the SVD truncation. So yeah, yes. No, so here so here the U and D won't be unique if you want. Yeah, but this is at least here I've not written any kind of normalization or anything. It's just it's just to introduce this. So this is equivalent to the thing. I will put a star to this problem here. And another way to phrase this problem is if you look at the vectorized version of A, then this problem is what? So, well, I'll write something and then I will comment. So this vec of A is just the vectorized version of so it's the vectorized matrix A. So in particular, this has dimension mn, okay, m times n. And so yeah, it's the minimum of the distance. And where u, the dimension of u is equal to k, and u is a subspace of Rn, and the dimension of v is equal to k, and v is a subspace of Rn. So you try to write the matrix. So you see the matrix A now as a big vector, and what you ask yourself is, can I write it? So this big vector, which comes from a kind of a product space, but that I don't see, and now I want to say what is, so how to write this big vector as a tensor product of k vectors from Rm and Rn. And so I mean, this is simply, well, this is kind of the same thing as here, okay? Because I don't know if I should have spoke about this, but yeah, basically when you write A like this, so here you write really A as a vector, whereas when I write its vectorized version, now this belongs to the space. Yeah, I need another color. Yeah, it's orange. Orange is better. So now this is in the space Mn. And so if I write the same thing, I have sigma I, but now I have the tensor product Ui Vi. Okay. It will be to speak about tensor generalizations. No, you have to vectorize now. No, here it's really as a, well, U tensor V would be no, now I'm speaking also. No, now it's these are vector spaces. No, it's, well, it's isomorphic to a vector space of matrices, but it's really a subspace of the product space Mn. Yes, I agree. It will become clearer when I will, because for tensors, then you would like to, maybe you would like to look at this point of view of the singular value decomposition. And but you will realize that it won't work. But yeah, I mean, because then, yeah, how do you generalize? Yeah, I mean, okay, it's the same thing, but yeah. No, here I'm, so yeah. So here, note that there's a difference. These are capital U and these are curly U and V. And yeah, the curly here means that it's a vector space. Yeah. Yes. Sorry. Yeah, lots of interrogations. So are there any yeah? I mean, yeah, writing, yeah, tensor vector spaces, yeah, drawing tensor vector spaces, it's, yeah. But yeah, maybe let's discuss that during the break. So I think it's a good, it's a good, yeah. So next will be a generalization of the SVD for tensors. Okay. Ouais, je pense, Julien, c'est bon. Right on time. Ouais, je crois que je l'avais pas. Attends, tiens, je vais regarder juste si. Ouais, ouais, s'il y a toujours des piles, parce qu'il avait l'air de fatiguer un peu. Non, ça va, on dirait qu'il y a 2 barres. Donc, il n'est pas sur nous. C'est bon. Non, je n'ai pas à changer. Okay. So let's resume. Basically, for the best approximation for matrices, we have kind of these 2 point of view. So looking at the best approximation by rank 1 matrices. So I want to write my matrix as a sum of rank 1 matrices, and the SVD provides me an answer about what I am missing of the original matrix when I select K of the optimal rank 1 matrices. I have also this subspace point of view where I try to look at my matrix as a vector belonging to this space. And I'm wondering how I can write this vector as a sum of vectors that are belonging to as a sum of k vector belonging, well, to this space and this space. So for tensors, it seems that it's natural to look at both generalization at first. So 2 generalizations to tensors. So we have 2 point of view. So as a sum of rank 1 tensors. So yeah, the tensor that I will look is a tensor, yeah, I will call it C, since I call it C in the beginning. And yeah, I will write it this. So I will yeah, I will take the particular example that we care about. So this big tensor of size 2 to the power L. So what would be a rank 1 tensor? Well, a bit analogous to this. I will write it as a tensor product of vectors. Okay. So what will be the analogous of the rank 1 tensor? It will be, for example, yeah, we'll write it this way. So it will be U1, tensor U2, so on and so forth, UL, where UI is just a vector of R2. So it's the tensor product of all these vectors is just an element of R2 to the L. And so the approximation by rank 1 tensors would be writing the tensor C mu, so C mu1 to mu L as a sum from 1, let's say, to K, U okay. So this would hold for all mu1, mu L. Okay. Okay. And where then UI, UJI belongs to R2 for I smaller than K and J smaller than capital K. Okay. So here the advantage of this format is that we kind of retain this low approximation. So if I look at how many coefficients I need to store to write this this tensor, I will need so the L vectors times the dimension, times the rank of my approximation times the dimension of the vectors. So the number of coefficients will be equal to 2 times K times L. So compared to the 2 to the power L, so here we call that this is 2 to the power L. This is quite great. So of course that's the thing that you would like to use if you wanted to do the best approximation of your tensor. The bad news is, we don't have such a theorem for tensors, okay? In the sense that we don't have so this you can interpret it as a rate of convergence if you view this result as a function of K. And the thing is, for a given tensor C, if you try to say what is the best approximation by a rank K tensor of my given tensor C, you don't have any kind of approximation result, and also it is difficult to select. So even if you know that your problem has a solution, it's difficult to select these vectors in a to determine these vectors in practice. So you have ways. Well, you have some ways to try to circumvent that, but it's quite difficult. Okay, so the drawbacks is that you don't have don't have a similar result than like the SVT. And also you don't know how to pick R or the vectors UI. Okay, so yeah, so it's a bit of a bad luck.
Then again, why the eyes are in option?
Because they only depend on one coefficient, so they just depend on the coefficient mu1, and you have just two of them.
Already at this level, so you say UI are two vectors. So why is that?
Because for mu, well, because I have two values for the mu's, so either 0.
Already this one.
So it's here I just so okay.
Okay. Already,
so here it's kind of and if I maybe to be more clear, so if I want to evaluate this at a particular index mu1 mu-l, this would be u1 of mu, well, it would be the product. Okay, so this is maybe clearer. And so in fact, each vector then is just a two-dimensional vector. How to pick, K. Yes. Okay. So yeah, for the subspace point of view, maybe I can already say that now.
what's going on if you do a ZD algorithm?
Yeah, I mean that's what you would do then. But I think there are some instabilities if the rank becomes larger. That's kind of but that's
What's going on if you apply a greedy algorithm? A greedy algorithm, you approximate C by one tensor product, and C minus this tensor product by another one product.
So I mean, another thing is that in fact this format is not closed even in finite dimensions. So I guess this would then be kind of then you would penalize the norms and so on. And so just before we finish with this format, so two things first. First, this format has a name. It's called canonical polyadic. Okay, so this approximation by tensor, by rank 1 tensor, it's also called canonical polyadic. Or CP, okay. So the CP format. And in fact, that's something that you already use in your quantum chemistry codes. I mean, it's it's what you would call the CI method. Okay, you just select some coefficients in some way, and then you would make, so you would approximate your wave function as a particular sum of Slater determinants, linear coefficient, well, linear what combinations? Yes, linear combinations of these Slater determinants. So it's in fact the CI method. Okay.
The link, because in the CI method, we select some determinants, but we don't decompose the coefficients into this form. Exactly.
I mean, you do I mean I think you do so just you do if you look at it as in the second quantization picture, I think.
Because you say the UI belongs to R2, so you assume that if it's occupied or not, the orbital will change. That's what it means. That's why you say it's the same thing, but it's like mu1.
Because here it also depends on the, you see, you have a dependence on the K, right? On the, okay.
Okay. Can we say that the rank, so if you have a CI with 100 Slater determinants, you can say that K equals 100, or?
Yes, exactly, yeah. Yeah, here, yeah. So, but okay, yeah. So it's not entirely a CI, no, it's but okay, it's not CI, it's related to CI, let's say. So, okay, in QC, related to CI. Okay. Yeah, because loosely. Loosely related to CI. No, but then you, okay, because, okay, to defend a bit myself, it's because you don't know how to pick this K, okay? And so that's why you try to come up with a scheme on how to select these coefficients.
Like, given a set of, so if I understand correctly, given a set of mu1, mu2, and so on, this defines one Slater determinant.
Yes.
Therefore, if you define a set of Slater determinants, you have a set of sets, but each coefficients are pretty good.
Yes. Well, here then you would put the coefficient in one of these UIs if you want. So all will be so if you want, you can put the norm here, and then the coefficient will be merged here. I mean, here what I could have added also is some coefficients. I don't know, CI here, for example, and have everything normalized then.
So
then CI would be is this vector either well, is this vector either 1, 0 or 0, 1? So is it occupied or not? And then this would be your CI coefficient, which depends on the states that are occupied or not. So yes, one Slater determinant would be one of these products.
So let's say U1 of U1, if U1 is 0 or 1, you should get two different results. I understand that as if you will have different orbitals depending on the location and functions can do it.
Yeah, it just means if you are occupying or not your
It's a function of our behavior.
Because you have two coefficients, that's it. So it's either, in your case, it's either 0 or 1, and you want, yeah, you have two coefficients. Okay. Yeah. So maybe let's speak about the second viewpoint. So this was the first point of view. Second point of view is kind of this subspace approximation. And for the subspace approximation, so basically you want to kind of see a generalization of this problem. So you would consider something like this. So you would like to minimize the distance of your of your vectorized coefficients to some tensor product of spaces. So the thing is, for this point of view, in fact, here I mean, here it doesn't make so much sense to take all equal to the same thing because in this case, since you are working with the tensor which is of size 2 to the power L, each dimension is 2. So here in the tensor case, what you can add is a kind of an index that depends on the subspace. So you can add here this extra dependence. Whereas here it doesn't matter because if one is larger than the other, what will matter is the size of the smallest dimension. This is because of the SVT, basically. So the thing is, if you write the solution to this minimization problem, what you have is that then the solution to the minimization problem so then it would look like this. So you could write the tensor as a sum. Should look a bit at my notes. So you would write the so as a sum of some core tensor times again a tensor product. So it would be yes, I will write it this way. So it's a bit cumbersome. Okay. So this is really the best. Yeah, it's a simu. Yeah, tilde. Yes. So this would be the best approximation. Yeah, the solution to the minimization problem. And so the thing is, I mean, you didn't gain so much if you look at the size of this tensor that you have here. This will be still kind of exponential in the number of sites. So you don't really gain something compared to this. So yeah. So that's, yeah. So this format has a name also. So it is called the Tucker format. And I had a quantum chemistry, kind of, yeah, which I've, yeah, kind of, yeah, I had a quantum chemistry interpretation of this format, which was, so I will write it in quantum chemistry, loosely related to MCSCF. But yeah, well, yeah, I guess you can, yeah, I agree. Then, well, I mean, okay, it depends what you call this, but yeah, to me, it's kind of, well, it's related, not loosely related, but okay. But here, yeah, it's related, in fact, to, okay, so I can erase that. It's related to MCSCF because then here, what you would say is that you would kill some of the orbitals. You would set them to unoccupied, so that you don't have any dependence on virtual orbitals. Okay, and so the core tensor that you would have here are the the MCSCF coefficients of your wave function.
K1 times K2 times KL is the number of spectral determinants that you have in your MCSCF. Because eventually you exchange the CU.
Yeah.
Some
Yes.
K1.
Yeah. Yes.
This is here.
Okay. 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 So these are possible generalization of the singular value decomposition to tensors, but as you can, well, as I was trying to say, I mean, and convince you at least, is that they are not the right generalization of the singular value decomposition to tensors, because in the end, what you would like to have is the best approximation result in some sense, and also to be able to characterize what you could gain if you increase your numerical parameter in your tensor format, and have something which is quite cheap to handle, not like this format. Okay, so that's why we need to look at the tensor train format. Okay. So tensor train that I will abbreviate TT. So it's again exactly the same thing as matrix product states. So in short, MTS. Yes.
For the Tucker format, you state that this solution exists, but is there a way to obtain it?
Yeah, there's the HOSVD algorithm. I think that's how it's called. Higher order. So given the tensor C, there is a way to retrieve these core coefficients by the higher order SVD. So in short, HOSVD. Okay.
An algorithm that can terminate in a for MCSCF, you need algorithm.
Yeah, but I think it's because also I mean, you are given also the ground state if you want. raz. So
It was specific, like, knowing the,
yeah, the full wave function.
there an algorithm.
Okay,
Order.
it's an approximation.
Yeah. Like SV.
Yeah.
Yeah, the way.
Yeah, approximating a given tensor. Yeah. Okay. So tensor train. So the idea of tensor train is to apply the SVD to a particular particular reshapes of the tensor. So let's introduce. Yeah. So the idea is apply successively DSVD to reshapes of the tensors. Okay. So I will just introduce the reshape that I will need. I think there's no need to explain it in great detail. So I have my tensor C mu, which is a collection of coefficients that are labeled from mu1 to mu(L). So reshape will be what? It will be a matrix. It will be a matrix that I write it this way. So it's a particular reshape, in fact, but yeah, let's say that for K, which is an index, then I write this reshape, which is a matrix of size 2 to the power K by 2 to the power L minus K. And at the bottom here, I will have my row indices. And at the top, I will have my column indices. And so it's a matrix. Okay. Yes?
So they're always ordered, like in the.
Yes.
Okay.
Yes. Yes, it's important. And so, yeah, so what I will do, so next, what I will present is the TT-SVD algorithm, which will give us the tensor train format. And so what I will do is consider different reshapes. So I will move indices from the top to the bottom. I mean, okay, so I don't go into the details in, yeah, to which operation it comes from, but I mean, if you take a Julia or MATLAB or anything, it's just a reshaped thing and that's it, okay? So I will, so that's why I don't want to spend any time on that, except just writing it as a matrix. Okay, so the TT-SVD algorithm. Yeah, maybe I should, okay. I will write it here, but I will write the algorithm in the next, because I need some space. So TT algorithm, okay. So the ID, and in fact the algorithm. So you start with your tensor, and what you do is you reshape it. So in the first step, you reshape it as a matrix. So it's a reshape as a matrix of size 2 times 2 to the L minus 1. Okay. And you do an SVD. Yeah, I will write it. Okay. So instead of writing sums everywhere, repeated indices at the top and bottom will be automatically summed. Okay. So I write it this way. When mu2 mu L. So this is the SVD of the matrix. Okay. So is this step clear? Okay. So now what I want to do is to kind of do an SVD of this, but before doing an SVD of this, what I need to do is a reshape. So what I do is I move the first index to the bottom, and I have my collection of indices in the column. So now I have a reshape of size 2. Well, so here, yeah, DSVD, yeah, well, no, I won't say what is the size, otherwise it will be too messy. So now I have my new matrix, and I apply again an SVD. No, up. So I apply an SVD, U2, alpha 1, U2, alpha 2. Yeah, yeah, I guess I won't introduce colors, otherwise, well, it will be clearer. Okay, so in the notes, there are colors to kind of see what is happening. So as you are going to guess, I mean, here, basically, you try to split all the indices, well, mu1 to mu L into different matrices, okay? So mu1 now only appears here, mu2 only appears here, and then basically you have kind of guessed the procedure. You just, so in this step, you have done an SVD, then you will do a reshape of this matrix, and so on and so forth, okay? So here, an SVD of sigma 1 V1 transpose. And yeah, and so here you do a reshape. So I just write this step just to alpha 2, mu 3, mu 4, mu L, and then so this is a reshape, and so on and so forth, until you are here. Up. And in the end, what you have is that you just need to do L-1 SVDs, and you have such a decomposition. And maybe I will write the one that appears here. Okay. Yes, yes. I have a sum that appears on the alpha indices. And so here, what I have done is just nicely split all the indices mu's to different tensors. Okay. And so this is the tensor train decomposition of my matrix C, of my tensor C. And so you have well, first you have the first result, which is that I have so given a tensor, I can build its tensor train representation. I have an exact algorithm that I can run. I'm not saying that you should run it, because the tensor that you have at the beginning is large, but at least you have a theoretical way to obtain it. So yeah, maybe I should write it. So here then it will be your tensor train decomposition. So this is the TT decomposition of C. Yep. Yes.
Yeah. Any questions? But if you do it in the other way, would it give the same result if you count from L?
So that's a good remark. You could, I mean, here I've started from the left, but I could have started from the right. If I do that, in fact, I obtain a different tensor train decomposition.
But are they equivalent? You can see that the sigma is for L minus 1.
They are,
Same object.
so they I mean, they represent the same tensor. It's just, but the tens, well, the objects that you have are different. No, here there's no truncation yet, but still you don't have the same. Okay. Okay, so maybe just just to write it a bit nicer than here. What is then a general TT decomposition? So TT decomposition. So it will be a decomposition of this form. So here, what I'm going to do is that, yeah, I can write it in yellow. Okay, so this thing, I will call it A1 of mu1, which has then an index alpha 1. Here, this thing, I will call it A2 of mu2, alpha 1, alpha 2, and so on and so forth. So it will be a decomposition of this form. And so here, as you can see, if I freeze, so if I pick mu1, mu2, and so on, here this becomes what? This becomes, so this in the middle becomes a matrix, okay? So you can see this tensor train decomposition as I have a row vector that I multiply by a matrix, that I multiply by a matrix, and so on and so forth. And the last one is a column vector. Okay. So you have row, matrix, 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 column, and so the whole thing it becomes a scalar. Yes.
Very stupid question. How do you put the indices mu1, mu2?
So here it's they are not selected. I mean, it's I write so this.
If I want to reshape my matrix in MATLAB or whatever, you need to know.
No, I mean.
So for example, if I start with a CI vector, so in my program, my CI vector is just going to be a long vector.
Yes.
The length of the interface.
Yes.
And so now you tell me that I need to reshape everything.
Yeah.
To tell you, but so I can choose one new variable if you want, but there is no guarantee that it's going to be the right one.
So here, what is important is that the mu they are really so is that the vector that I'm starting from is a tensor in the sense in the sense that the dimension here is a product of dimensions. And so I have really a first index, a second index, and so on and so forth.
So it's like the site of the site.
Yeah, the site, yeah, it's the site indexing.
Interesting about it. Yeah. So for example, you would take like mu1 from 1 to 2, mu2 from 3 to 4. That's the problem. Yeah. So it depends how you truncate and how you reshape this matrix. You have a degree of freedom.
Yeah. Well, yes. Yeah, we agree, I think. Yeah. I mean, we have you have a degree of freedom in how you order these indices. And this, okay. I was going to talk about that, but yeah, it has an influence. Yeah. Are there other questions? Okay. Yeah, so to come back to the TT decomposition that I was writing, yeah, so the TT decomposition, so it will be the collection of A1, AL, such that this is true. And where AK mu K, it's a matrix of size Rk minus 1 Rk, and the first index and the last one are equal to 1. Okay, and in the middle, since it's just a matrices, it's just a product of matrices. Okay, so the picture that you should have in mind is that, so this holds for all coefficients. And the picture that you should have in mind is that this C mu1, mu L, these coefficients, it's equal to one column vector that is multiplied by some matrix that is multiplied by another matrix until some column vector. So yeah, so here it's a column vector. Okay. Okay. So yeah, so by the previous algorithm, you have an exact representation of any tensor. So maybe we can state some properties. So properties, any tensor, yeah, okay, I will write this. Any tensor has a TT decomposition. So this is kind of nice. Yeah, the ranks here. So, well, I call it rank. So the RK, yeah. So this here, well, I call it TT rank. But in the physics literature, they prefer to call it Baum dimension. Okay. So it's exactly the same thing. Now let's speak about the cost of storing this format, cost of storage. So the cost of storage, you just need to keep all these matrices. So for each one of them, you have two versions, okay? Because mu k is equal to 0 or 1, so you have 2 times basically Rk minus 1 times Rk. So the sum. Okay. So Rk equal 1 to L. Yes. And so this is then the go max of the Rk squared. Okay. So now, yeah, the big numerical parameter in this, yeah, finish just, yeah. The big numerical parameter is this rank, this bond dimension. So if you are able to show that the object that you handle has a small bond dimension, then you know that you have a sparse way to represent your original tensor C. Yes.
Which is anti-symmetric.
Yes.
So here is the coefficients. It seems to me that they are on the basis of symmetry, not on symmetric function.
Yes, yes, that's what happened when we went from this, from the n particle sector, the n particle for the n electronic sector, fermionic sector, to this Fock space picture. So by doing this, you increase the dimension, but yeah, now you just have a big tensor that you want to represent, and you don't have well, you should have a particle constraint on the tensor that we ignore, but that's it. Yeah.
When you get approximate wave functions, are they anti-symmetric or almost anti-symmetric?
No, so what could happen is that you get in the end a tensor which doesn't live in your n particle sector. So which has some components that are n-1 or n+1 that has, yeah, n-1, n+1 electrons.
So it means that your calculation is not right.
Well, it's related to the format that you are using. It's ignoring the number of particles. So, but so if you do it in a good way with by taking care of that, you shouldn't have this problem. But if you don't, yeah, if you are ignoring these aspects, yeah, you can have an approximate solution which doesn't live in the right space. Yes. Okay. So yeah, another thing is yeah, so it's properties and it's also remarks. Okay, properties, remarks, remarks. So another thing, you can notice that if I am given a tensor train decomposition of my tensor, here I can insert any invertible matrix and its inverse to and obtain another tensor train decomposition of my original tensor. Okay, so 3. The TT decomposition is not unique. So in the sense that, yeah, if I consider my original decomposition, and I insert, yeah, we'll call him G1, G1 inverse, G2, mu2, J2, J2 inverse, so on and so forth, until JL minus 1 inverse. Okay. Then if I define this as A1 tilde, mu1, this one as A2 tilde, mu2, and so on and so forth, until this one. Then I obtain an equivalent tensor train representation, which is exactly of the same size, by the way. So then A1 tilde, A8 tilde is an equivalent TT representation. Okay. So I mean, so it looks dangerous, but in fact, there are ways to handle that. So basically, it means that you need to set extra conditions on the tensors that appear in your tensor train decomposition. And so if you set the right conditions, then you are fine. So numerically, it's not an issue. So need extra conditions. on 80 there, but it's in the end it's fine. But it's important to note that. So now, just yeah. So just maybe two things. First thing, yeah. So here, yeah, when you look at the algorithm, let's see a bit what these TT rank or bond dimension is related to when you look at the algorithm. So if you look at the algorithm, so you do successive reshape SVDs, reshape SVDs, but if you look at the reshapes, they are kind of compatible, okay? So, oh no, maybe let's speak about, let's speak first about R1, okay? So what is R1? Okay, R1 is the dimension of this matrix here, okay? And where does it come from? It comes from the first SVD, okay? So what is R1? R1 is exactly, the rank of this reshape, okay? So if you look at, let's write that. So what are the, okay, so R1, this is exactly the rank of C mu1, mu2, mu-L, okay? Now let's look at R2. So that's where it's a bit maybe trickier, but if you look at R2, R2 is related to the SVD of this part. But here, when you do the SVD, this is an orthogonal matrix. So you can convince yourself that if I have done, so instead of doing the SVD of this one, if I have done the SVD of, so at this step, if I have done the SVD of this reshape, so kind of collect this into the sum over the alpha one and done the reshape of this matrix, then I would have obtained, so I would have obtained the SVD of this matrix. And in fact, another way to see that is just to check that the matrix that you have here as a, with mu1, mu2 as a row index and alpha 2 as a column index is indeed an orthogonal matrix. So exercise. And in that case, what you obtain is really the SVD of this reshape of the matrix. So R2 is in fact the rank of the reshape of this matrix. And so in general, what you have is that RK, so this was by the first step in TT-SVD. And so in general, RK is the rank of the matricization mu1, mu-k, mu-k plus 1, mu-L. Okay. So, so the thing is, and this is, I mean, it's not a magical format. You have exponentially, you have an exponential number of coefficients here. So for a general tensor train decomposition, you cannot have something which has which has much less coefficients. So if you look at this rank in general, you can still expect to have exponentially, to have an exponential rank with respect to L. Okay, so in that sense, you haven't achieved the dimension reduction. But the thing is, if you look carefully at the TT-SVD algorithm, so you know that at each step you do an SVD. And you know that you are doing the SVD of a matrix and that you have this theorem that tells you for matrices that I have a best approximation result by truncating the SVD. So what I can choose to do is to truncate the singular values if I think that they are too small for my approximation, okay? And so this gives me an approximate tensor and an approximate tensor train representation of my original tensor. And so what is the deviation with respect to my original tensor? Well, it is simply the error that I make at each SVD truncation. And this is because of the theorem of the best approximation by SVDs for matrices. So the approximate tensor train that I obtain by truncating at each step my SVD will just be related to the singular values that I throw away. So what I can have, so at each step, well, one can truncate the SVD. To, let's say, so two ranks that I will call, I don't know, R1 tilde, RL minus 1 tilde. And so now, if I look at what is the best approximation in the Frobenius norm, this will be, so it will be simply the sum of the singular values that I throw away at each step. So it will be, yeah, so I write a formula then. So the sum from 1 to n minus 1, I, which is larger than R tilde j, and sigma I, j, so I are the singular values of what? So, I mean, this you can kind of guess. This will be related to the singular values of the reshapes of these matrices, which are related to the ranks of my representation. So of C, mu1, mu k plus 1, mu L. And here, this thing is simply the TT-SVD truncated at each step. Well, at SVDK. And the thing is, yeah, I still have a lot of time. The thing is, and well, this you can kind of, well, the thing is, this bound is sharp in the sense that here it means that if I look at the best approximation of a biotensor train with these ranks, then it's bounded by this sum. And in fact, I have also, this provides a lower bound to the best approximation. So you have a lower bound of C minus, well, yeah, TT R tilde C. So it's not the same, but yeah, yeah, in the Frobenius norm. Yeah, we'll put a tilde where this one, it's the best approximation. So what this theorem tells you is that the decay of these singular values is really the thing that you want to monitor, to be able to assess if your approximation is good or not. Okay. So again, like in the matrices, you want to look at the singular values of all your reshapes of all these matrices for k from 1 to L. Say that these singular values decay fast, and if they decay fast, you have a good approximation by a tensor train of reasonable size. Yes? Yes?
Say that Fk is the rank of
This reshape?
so it should have some. Its form should be something like.
Yeah. So the yes.
But I didn't really see how it feels. So I didn't see, for example, what's the decomposition of zero?
Of zero. What do you mean of zero? So we'll do TT some TT decompositions. Yeah. So what this tells you is that if you plot the ranks, so yeah, so this is R tilde K and this is K. No, RK, sorry. Then it kind of should look like this. Okay. And then the thing is here, yeah, let's say that L is equal to 2L, okay? Just to, so here, the value that you have is 2 to the power L, okay? Because it's so this is for capital L, so this is for 1, this is for L over 2. And because the matrix that you have here, it's C mu 1 mu L plus 1 mu 2L.
But why are they of maximal rank?
Ah, they don't have to be. They don't have to be. This is the maximum. So this is the yes. So this is the maximum, and you hope that the state that you approximate will have these ranks. Well, at least the approximation will have these ranks. Yes, or something that is negligible, and so that's what you hope for. Yes.
So don't make any approximation if you keep the ranks.
Yes.
Is it possible that the number of parameters in your tensor train decomposition is larger than the number of parameters of your tensor?
I didn't look at that, but I guess you will have to do the sum of all the coefficients to see if it's true. Maybe, yeah. I guess, yeah, I guess it should be true because for the SVD, if you have a general matrix, well, if you are counting really the value of the coefficients, then you have more coefficients in your SVD than in your.
So redundant parameterization.
Yes.
But then you hope to be able to
yes. Yes. No, I don't think so. I think it's really by it's well, numerically you would just try to minimize this norm and then try to but yeah, I don't think there's a way to write the best approximation. But you just know that you are within this range, okay? So yeah, and something interesting. So here it's L minus 1. So if you take L equal to, which corresponds to matrices, then this gives you the sharp bound that you have well, that you had previously for matrices. Okay. So I have 15 minutes.
Question.
Okay.
So if you want to reshape C, you need to have something in C at the start. So what do you put in C?
Yeah, so, okay.
So when you start to calculate. Second question is like, when you look at DMRG papers, they always say that if you want to converge to the full TI value, you have to extrapolate your results to infinite bond dimension.
Yes.
But to me, it looks like the bond dimension is a finite.
Yeah, well, I guess, so I think, okay, there are two things. So for the first thing, you would start from a Hartree-Fock reference, for example, or a low, for example, or a CISD or what, something manageable.
But how do you guess your coefficient? Are they the product of the molecular orbital coefficient?
Yeah. So, okay. And the one particle basis are your Hartree-Fock orbitals. So basically you start with the tensor, which has only one coefficient, and then you go, yeah, and then you run your DMRG algorithm to go beyond that.
So you increase the size of the tensor?
Yes, and you hope that you converge at some reasonable value of the bond dimension.
But in what you explained here, you assume that you know at first the coefficient of the wave function, and you just want to get try to find them.
No. Yes, it's more to motivate the format. Although what I can say is that if you have, for example, some tensor train representation of your tensor, which is not optimal, but let's say you have a tensor train representation, but you want to compress the representation, you can adapt this algorithm. So I won't do it, but this is something you can do. And yeah, maybe for the second question, I think it's related to when you want, so when you are doing, so when you are also increasing the number of sites also. So you are increasing the number of sites, and then if you increase the number of sites, then the rank also goes to infinity, and so that's why you do this extrapolation to infinity. Yeah, well, then I guess infinity is because exponential 2 to the L is, well, 2 to the L is very big, so it's infinity. Yeah.
Because you want to consider the direct.
Yeah, I guess that's what that. No, it's not infinite.
Once you truncate something, you make an approximation at one state, but you will never be able to recover from.
No, that's why you hope that you don't make a big error. And so that's why you, yeah. Yes?
So, two questions. So you can also put one down.
I mean,
so one thing, when you do the truncation, do you use particle
yes, you can. Yes, you can indeed. Yeah, you have to do it in the right way to not lose particle conservation. Yes. Well, I guess so in the MRG, you wouldn't do this. What you would do is you would minimize within using the quadratic form defined by your Hamiltonian. So, which, yeah, that's what you would do. And so in this sense, you would approximate in the right energy norm if it converges to the right thing. Yeah, I could have said that. So the cost of an SVD is, so cost of an SVD. So Yeah, I know the cost of a full SVD, but cost of a full SVD. So if I have a matrix of size m times n, then the cost is so here I don't assume that the rank is small, so it's m squared plus n squared. So it's something like that. So here it looks cubic. It's not great, but I think that if you consider the truncated SVD, so then I think it's like KMN, I believe. No, it grows quadratically with R. But and that's why you hope that R is smaller. Or maybe cubically, but yeah. Okay. Yeah.
And maybe for the R1 would be equal to 2.
Yes. R1 would be equal to 2 generically, yes.
And if one refers, let's say, if you think about the CI, U1 refers to the core orbital, which it always occupies it. Then that rank becomes 1.
Yes. Yes. Yeah. Okay.
So the maximum value of this RK, that is related to the Hamiltonian X.
Well, yeah, because the wave function that you're interested in is the ground state of your Hamiltonian. So yes.
Electron repulsion is super local. Probably this kind of method works very well.
Yes, yes. So this will be in the Hastings area law. But yeah,
okay.
Yeah. Yes. Okay. So I think I want to finish with 2 things if I have time. So first thing will be, yeah, so I will introduce it now. It will be the graphical representation of tensors and where this name tensor train comes from. Okay, graphical representation. So for the graphical representation, yeah, so basically it's kind of like any kind of graphical representation. You have a dictionary. So the dictionary is the following. So if I have vector v, then my vector v is just coefficients vi. And so the graphical representation will just be some node with a free leg, okay? And so the free with the free edge, I should say. So the node represents my vector v, and the free edge is the index, so the degree of freedom that I have in v. Okay, so this is for a vector. For matrix, now I have 2 indices. So maybe you have guessed, but to represent this, I have so my tensor, well, my matrix is represented by 1 node, and I have 2 edges, which represent the 2 degrees of freedom that I have in my matrix. Okay. So if I have a general tensor, like the C mu that I have, mu1 and mu-L, then what I have is the tensor C with as many legs. So mu1, mu2, mu3, so on and so forth, mu2. Okay. I have as many legs as I have indices. So it's a convenient way for the moment just to see what is the, well, so the number of indices is what we call the order of the tensor. Okay, so this L here, so it's something that I could have mentioned earlier, is what we call the order of C. So L is the order of C. Yeah, so here it's doesn't look that great as a dictionary, but the interesting part is that you can write matrix vector multiplication. And the way you write the matrix vector multiplication AV, for example, with index J, is by kind of combining the sum, well, the sum, the indices where you sum. Okay, so here I sum over I, and so in a graphical way, this sum here I represent this way. So I have a V, A, and I have a free index J. Okay, and the summed index here is the index I. Okay, so when two nodes are connected by an edge, it means that there is a sum that is behind. Okay. I think I don't need the TTSVD, so I will erase that. Okay. So now let's write the graphical representation of the tensor train decomposition. Okay, so I have my tensor C. So on the left-hand side, I just have this. Okay. And now, if I look at my first, so at A1 only depends on two indices, so mu1 and and the shared index here in the sum. So I have A1, which has a free index mu1, and the shared index with its neighbor A2. Okay. A2 is a matrix. So A2 is a matrix and it depends on mu2. So I have a free index mu2 and the summed index with its neighbor A3, and so on and so forth. And the last one, I mean, you have just the sum with the previous matrix here and the free index mu. So yeah, so in a nutshell, that's why it's called kind of tensor trains, because you have kind of the wagons. Okay, voilà. Yeah. So thus the tensor train name. Yeah. So yeah. So the graphical representation, it will be quite useful when I will speak about DMRG, because it will simplify the discussion. And here, yeah, basically that's the dictionary you need to kind of make the mapping between formulas and the graphical representation. Yes. Yes, it's because here when I write it this way, it's for each mu k, this is a matrix. And so AK has 3 degrees of freedom. Okay. So yeah, I think yeah, I had an example, but yeah, I guess we are closely, we are too close to the end. So yeah, tomorrow I will start with an example highlighting the importance of the order of the indices in the tensor train decomposition. Okay. Thank you. Hop. Alors, je le mets sur mute.